Have you ever stopped to think about how an AI predicts something as incredibly chaotic as the weather? Well, today we're going to break down a really cool breakthrough that's teaching AI to find a smarter, way more direct path to the future. Let's get right into it.
So at the heart of this whole thing are two totally different philosophies. You've got the old way, which starts from pure random chaos. But then there's this newer, much more intuitive approach that asks a pretty simple question. What if we don't have to start from scratch every single time?
Before we jump into the solution, we really need to get a feel for the size of the problem we're trying to solve. And honestly, there's no better example than the beautiful, swirling, and just mind-bogglingly complex chaos of our planet's weather.
I mean, this is the core challenge, right? Physical systems, like our climate, are run by these incredibly complicated rules. We're talking about things like the Navier-Stokes equations, and they have just countless variables, all interacting at once. Trying to forecast all that is a huge computational lift that pushes even our best supercomputers to their absolute limits.
So how do most of these powerful AI models, especially the diffusion models you've probably heard about, even attempt to tackle this massive task? Let's take a look at the standard playbook.
At their very core, you can think of these things as learning machines. They chew through enormous amounts of data, like decades and decades of weather maps, and they start to learn the underlying patterns. The real question, though, is how they use that knowledge to create the next thing in the sequence, like the weather map for tomorrow afternoon. The usual way is something called a denoising process. The AI literally starts with a screen full of pure, random static. Then, using today's weather as a kind of guide, it carefully refines that static, step by step by step, until it slowly transforms into a prediction. Think about it like this. Imagine telling a sculptor to create a statue, but every single time you hand them a completely new, random block of marble, even if they're just trying to change the pose slightly. Yeah, it works, but it's not exactly the most direct route, is it? So on the one hand, we've got this established method. It's powerful, for sure, there's no denying that. But as this research points out, it might just be a really inefficient, roundabout way to get from today to tomorrow. So, what if there's a better path?
And that brings us to the star of our show today, a technique called stochastic interpolants. And this really represents a fundamental shift in how we think about modeling these complex physical systems.
The big idea from the research is spelled out right here. Instead of starting from total randomness every time, why not just learn the direct path from point A to point B? Why not teach the AI how to transform the current state directly into the future state?
So instead of thinking about that sculptor with a new block of marble, think of an artist who already has a sculpture and is just making small, precise adjustments to change its pose. The model learns the change itself, that direct path between the two states. And that's the crucial difference. The stochastic interpolant method uses a simple but really powerful truth. The weather 6 hours from now is way more similar to the weather right now than it is to a field of random static. It's just connecting two dots that are already close together, which it turns out is a much easier and more efficient job for the AI.
Okay, so it's a clever idea, but does it actually perform better in the real world? Well, the researchers put these models head-to-head on some really tough challenges, including global weather forecasting.
And this is where it gets really interesting. Let's look at the hard data. For a 5-day weather forecast, the standard model had an error rate of 26.5. But the stochastic interpolant model, it came in at 22.9. Now that's not just a tiny bit better. In the world of meteorology, that's a huge leap forward in accuracy.
But here's the real kicker. It gets that higher accuracy while being much faster. The research shows the SI model only needs 5 sampling steps to make its prediction. The standard model needed 10, and some other models can need up to 100. We're talking about a massive improvement in efficiency.
So, here's the bottom line. The stochastic interpolant method isn't about making a trade-off. You're actually getting lower error, which means more accuracy, with way fewer steps, which means much more speed. It's a true win-win. You're getting better predictions, and you're getting them faster.
All right, so what does a faster, more accurate AI model really mean for us in the real world? Well, the ripple effects here are actually a lot bigger than you might think.
The implications are huge, really. For us, it means faster, more reliable weather alerts. For scientists, it means better tools to simulate everything from turbulence in a jet engine to the long-term effects of climate change. At the end of the day, by teaching AI to take this more direct, common-sense path, this research sets a powerful new standard for how we model the physical world around us.
And that leaves us with one final fascinating thought. This more intuitive A to B approach isn't just for weather. If we can apply this to something as complex as the atmosphere, what's next? From modeling financial markets to understanding intricate biological systems, this smarter path could unlock whole new frontiers in AI-driven discovery right across the board.